Welcome, everyone. We're here on Tuesday, September 16th with Martin van der Brink, the President and CEO of ASML. Martin, we're so glad to have you here today. ASML is one of the most significant companies in the world today. In fact, I like to think of it as essentially the one company that is keeping Moore's Law alive. Could you tell us a bit about your early years and what it was like growing up, and then if you had any hobbies or special interests, what your parents were like, that kind of thing?
Yeah, so first of all, I made it public that my skill set was not broadly developed in the early days. I was dyslexic, so that handicapped me a bit at the beginning to get to through college. So I got a special track in the Dutch system where I did go through what I call technical education, like lower technical education, middle school, high school, and then end up to university. So by the time I was in university, I was already past 20 years before I started my study physics. So I had instead a lot of interest in making things myself, having your own moped stuff, making construction changes in the house. So I was pretty much hands-on at the beginning, consistent with my early education.
Right. And when you were studying physics, can you tell us what attracted you to physics?
So, good question. So if you're looking through the Dutch education system at the start, I couldn't start with physics, so I started being an electronic engineer. So most of my education is in electrical engineering. But I found at the time, as an electronic engineer, you taking a catalog from Motorola and TI and look into the chipset and the transistors, and then you combine the things. Mm-hmm. For me, at the time, there must be a world behind those components, and so there must be a broader world to investigate than just connecting components and connecting wires. Mm-hmm. And that brings me to do physics, to have a bit more broader background. That's why I choose to be physics for my master and bachelor.
Any specific aspect of physics? It's a very large.
Good question.
It's a very large field, of course.
Yeah. So I'm not a theoretical guy. Also, given the background I just explained, although I'm very hot on solid theory, but I'm not approaching my work or my study from a theoretical point of view. Now, when I started studying physics in the 70s, late 70s, in fact, I started in 1980, it was the first energy crisis, so my master's thesis was around district heating, and which has nothing to do with which I did during my first job at ASML. In fact, it was one of my handicaps applying my job. But more or less, I was much engaged with the energy crisis, so I felt I have to do something good, so I did district heating. And believe it or not, at that time, I learned a lot about thermal modeling. And believe it or not, today, when you go to advanced steppers, its accuracy is for a large part be determined by how well you deal with the thermal issue. So at the end of the day, I still could have a solid piece of my education being applied at ASML, although I have to do quite a catch-up on optics.
Yes, exactly. We're going to get back to the role of optics in your machines, which is absolutely fundamental. Would you like to tell us a bit about, once you graduated from college, what were your first jobs, and how did you end up at working at ASML?
It's very simple. I did my master thesis on district heating, and I was supposed to graduate in January, so I started looking January 84. And late 83, I started looking for a job. And like many people, you apply with the big companies like Philips, like I did, been invited. Toured around at Philips in fall of 83. And then the business unit I was too old to be hired for research. So research at the time at Philips were just younger people. I was 26 at the time, given my education before. So people at a certain age, you're not going into the track into research. I was the track in industry, and the industry unit was, the business unit was science and industry, which include the lithography division.
Can you tell us how, was Philips a major player in lithography, or is it just Philips?
No,
it was
no, that's another part of the story, which,
okay.
which we should go back a bit earlier.
Sorry.
But, you know, you talk, how do we get there? So I toured around that company, looked at the various things, and I was not interested. They'd like to push me into the software, given my software degree also. As part of the district, you did a lot of simulation. And I didn't find it interesting. And so I was ready to go back home and without a job. And then Wim Troost, one of the executives, showed me the brochure of ASML. I looked for the brochure. I said, I'll take that. Well, I'll see you in March. That's how it went. So it was the last minute. So I didn't talk to my potential boss or to my colleagues. I've just been hired into ASML.
Now, can you explain for people watching who this man was? Wim Troost?
Wim Troost, yeah, and his boss, George de Cruijff. They were also the two guys who were working with Arthur de Prado on the joint venture. At the same time I was working, because they showed me, so you can do this. But you will not, if you do this, you will not join the big company Philips. You will join this joint venture. And I was not at all distracted by that. I said, I'd just like to do a complicated system. And this seems to have many aspects which interest me. So that's why I took on the role.
Right. And what were your first tasks at your new job? What did you work on?
Well, in '84, when I joined, we just had the joint venture between Philips and ASMI, and we were about 50 people, the whole group, 50 people, completely overwhelmed with the task and not successful. We had, until then, there were only systems operational at Philips at the facilities in IMEC and Hamburg, and we had one system at IBM in Burlington, which was also not running well. So that was the environment I joined. And so the first task, people tried to hire me. We were having a 4-inch wafer machine, and the idea was 4-inch is good for now, but we need to get to the next milestone. We need to go to 6-inch. And most customers did not go with us because we didn't have a plan for 6-inch. And I was supposed to be responsible for the alignment system and the radical management system at the time.
And the alignment system does what?
Well, if you, the whole trick in litho, I call it almost, there are 3 things in litho which are important. It's first the imaging. If you don't have the imaging right, forget about it. No need to think the next step. If you don't have your imaging right, stop at it. In fact, productivity 0 of the machine would be the best. And then you go next. If you have the image, you need to be in the right place because you have the image, but it needs to be built up a 3-dimensional structure. So the images, subsequent images need to be aligned to each other. And if they're not aligned, you cannot connect. So the alignment accuracy need to be a fraction of your smallest feature, which is called overlay, and alignment is part of that subsystem. When you don't get that right, it's a no-show. When you get the imaging and the overlay right, now you like to have as many of them as productivity. Those are the 3 things in lithography.
On the aligner, just to dig a little deeper, does it rely on like fiduciary marks on the mask, or how does it go ahead and align?
No, we call fiduciary mask on the wafer stage. So what it is you align. We were at the time be known for through the lens alignment. That means we aligned the mask directly to the wafer. So we didn't depend on fiducial in the beginning. We changed it over time differently, but that time was through the claim to fame was you go for the mask to the wafer direct. That means you have a direct reference of your wafer to mask.
Okay. Just to set the competitive landscape at this point, can you tell us who you were competing against at this point?
Well, we had, of course, Perkin-Elmer, which were so successful with the microline. I'm sure you must have that also in your history center. It's an amazing machine. Where they launched it in '73, Philips had their first research prototype in the lab, also around '73. And when I joined, people bragging about how stupid this Perkin-Elmer system was and how advanced we were. But the real issue is the market was not ready for the advanced stepper, so that time in the '70s to '80s, we have one-to-one projection alignment, which is such a simple machine. You could earn that machine back in a few months. So it was a very successful program, so successful that Perkin-Elmer had an issue by preparing in time the next step, where GCA, Nikon, Canon, and later on also ASML jumped in.
Excellent. And the Japanese?
Nikon and
Canon. Canon?
Canon also. Canon, I think by the time we started, we had GCA. Perkin-Elmer was not playing a major role. In fact, Perkin-Elmer has tried to acquire ASML ahead of ASMI, which didn't fall through, and he ended up with Sensor and Liechtenstein, which never really took off. So the real competitor we consider GCA, Canon, and Nikon, and GCA quickly wasn't able to follow the market, and so for the largest part of time in history, we have Nikon and Canon against us, and then the other like Co-Build and AZ, a few other, Hitachi, they never played a substantial role.
Well, one thing I'd like to pick up on, which was I think a quote from you, don't worry, in Focus, where it essentially says the machines are delivered. I don't want to be careful what word I'm using, but still requiring some on-site configuration. And that I thought was really fascinating because of the blend of multi-domain knowledge, optics, electronics, physics, maybe some psychology, who knows.
Well, I do have psychology minor also in my study. I did take it on interest, so was part of my education.
Yeah, very good. Yes. Well, I think it's useful.
People try to get me MBA knowledge, like the numbers. I thought the numbers were not interest, so I had to go to philosophy and psychology as a side specialization.
Oh, I think that's a very good choice, actually.
We will learn the business when we deal with the business.
Yes. Now, I want to touch upon a point here about IMEC and your relationship with them. Can you tell us a bit about this? Because you were...
so it's a very good question. So on the application, I was a machine guy, and probably I learned a whole bit during my career, but I'm still a machine guy, right? So it's metal and optics and motion control and
as
all that stuff.
As opposed to software, let's say.
Yeah, but software also.
Yeah.
Software. I had a minor in software also at the time. At the time when I was educated, you didn't have computer sciences at that time at the university. So what you then did, you did physics, and then you had a minor on mathematics or numerical mathematics, or you're making software programs. So I made a lot of software program when I was studying, but not to the business. But I'm still a machine guy. And I found out that in order to get a system working in a fab, it needs to work with the mask making, with the resist, the wafer track, and it needs to have a certain yield and all that stuff. And there we had no clue. And there I think our initial work with IMEC, which happened to be attracting a substantial amount of major customers on their premises, we're exercising with our most advanced system to understand the capability. And that has helped us enormously broadening our understanding on how the systems were used in the fab prior of learning this from our customer directly. And this working with IMEC was founded about the same year as ASML, 84. And our success and the success of IMEC has come together. I would still consider today IMEC as probably the biggest institute where all major customer comes together. Of course, they could not scale the business as we did on steppers, but we could say we drove each other's success almost jointly.
So was IMEC a place where, help me understand, where were companies from around the world or just Europe?
Yes, no, around the world.
Around the world.
You have Samsung, TSMC, Hynix, Intel, Micron, all are participating.
And would they get to use the equipment and try it out? Is that the idea?
I think that's a big word, to try it out. Our machines are used to do that process development. So it's not that engineers are looking to our machine. No, they doing into process integration for their pre-competitive phase on the next chip. And by doing so, they need to make exposure, and our system was there to make the exposures. So we were always part of that advanced processing. And then those engineers were often on an assignment to IMEC, moved back to the main company. And when the equipment selection came to play, that plays, of course, always a certain role that they were used. Some of those guys were used to the ASML systems.
Right. And for people who don't know, IMEC is a Europe-wide institute funded by the EU.
Yep.
Is that right? Yeah.
By government, also the Flemish government. But it's also funded by customers. Yeah? So it's not that they just a substantial amount of money is being attracted from their customers. And today, it's also major companies like the fabless guys who like to understand how chips are being produced.
Right. And now, tell us about, just to get into physics a little bit, I'm thinking back to, when Robert Noyce apparently went down to a camera store in San Francisco and got a couple of 16 millimeter projector lenses, and that was his first, that's how one of the earliest ICs were made. So you compare that to is it almost 1 million parts in a current ASML lithography machine?
Yep.
Maybe. And the cost and the size, and it's just it's an incredible journey that lithography has taken since the earliest days. And I'd love to get your thoughts on this. Is a bit maybe future oriented, but we'll come back to the history. But do you see an endpoint to lithography?
An endpoint.
An endpoint. Where the physical limits are reached. And
so this may sound a bit arrogant, but I think the technology of litho is unlikely to determine the endpoint. It's very likely that but this is now a very future-oriented question, where the chips are going is going. So when we are, if you look into the history of chips, where the overall law is what we call Moore's law. Underneath Moore's law, you have is it the memory guy? Dinar scaling. Dinar scaling. Robert Dinar from IBM, the DRAM guy, who made a very simple assumption: if you make things smaller, things get cheaper, things get faster, things get less energy consumption. And this has, for the first 40 years of chips, has been the success of chips, that everything gets so much better. And this lasted till 2000, the mid-2000, 2010, where the power density was getting to its limit, so you could not increase the clock frequency. And every time you go smaller, not everything comes your way. So then you have the multi-core. Today you have 3D integration. So what we see, Mark Liu of TSMC, supported by a Stanford professor, can't remind his name, did make a publication in IEDM where they say system scaling likely continue to at least 2040. 4.0, and is able to deliver the system. But it's not only from lithography, it's also for system integration and stuff like this.
Like chiplets?
So it's and chiplets. Yeah. And it's well thinkable. What we're seeing today is the shrink rate is reducing, the physical shrink rate, but the system integration effort is expanding. And so it will be that we'll continue to scale at least for the foreseeable future, at least 10 years from now, 15 years from now. and that the lithography scaling itself will continue to slow down. And we could well be the case that there is no real need of going to lower wavelength, given the future of shrink.
It seems like, and chiplets make this rather explicit, that you can optimize the node you're designing at.
Yeah, but there's much more needed for chiplets because the EDA guys need to step up and still make sure it does the 3D system optimization, which is the current NVIDIA high-end chips are the best you can provide. But from a theoretical point of view, it's not the best architecture you can have. So what you every time see that the industry is consolidating itself on certain technology and work on this technology as long as it can and then wait for the next disruption. So more disruptions are needed and will also happen the next 10 years to get to the next level of performance of compute.
Right, and I guess you'd probably agree with this, that there are tons of applications where you just don't need the latest node.
This is endless.
Perhaps the majority of them.
I'm a bit aggressive here also in my language. The current AI is almost lazy and prefer to extend the model size and prefer to add learning cycles rather than simplify the model so they can do less learning cycles. So we spoil the industry with high performance compute and they take it from a hose. But this is long term very difficult to sustain given the overall energy consumption and a few other things and cost. Long term this becomes an issue. So we need to work on also not only system optimization on the computer system, also on the efficiency of modeling is important. But at the moment the chip, and that's why AI is good for the high performance chip, at the moment the chips could provide real value in terms of energy consumption and speed, the market will take it because it allows them to expand their model size, and which is the cheapest way of gaining AI intelligence, or the cheapest, the most effective way to date.
Now, you worked on a machine, I believe it was called the PAS 5500.
Yeah.
Is that right?
Yeah.
Can you tell us about it? Was that your first major project?
Yes.
Yeah, tell us about that.
So, in the 80s, when I joined, I was in a land of blinds where if you have one eye, you win. So there were 50 people. And I just could develop, I'm very lucky, I could develop very quickly as a lead engineer and developing, be part of the PAS 5500, the PAS 2500 team, which is supposed to be delivered to Philips in January 86, 2 years after I joined. But you start from a university, have no clue about litho, and you need to develop a complete machine in 2 years, which was not under my complete leadership. I did only do the alignment of reticle management system. So, and I published this on my first publication, SPE, in the microlithography, and back in 85, my first visit here of 86. My first visit was in 85. Within a year after my appearance here in Santa Clara, in the Marriott Santa Clara, we had our SPE microlithography meeting at the time. And I changed the alignment system, but I also changed the mask handling system. And I was proposing Smith boxes at the time.
What is that?
Smith is a standard mechanical interface invented by HP.
Oh, Smith.
And the guy doing it may he appear Perick. He may be on the History Center as well, I guess. And he took it off as a spin-off of HP and developed Smith boxes, today used for wafers. I was adopting that concept for masks. It was one of the innovations we had on the first 2500.
So your machine had to accept Smith
yes.
boxes.
Yes,
yeah.
But it was not done by anyone else. And also recognition that defects, or mask defects, were of course extremely critical. It was at the same time we started to use pellicle on lenses, but we put them in Smith boxes to be more protective.
Right. Now, one thing that really surprised me was the expense of the masks. How incredibly expensive they are. Is there a reason? Well, obviously they have to be perfect and extremely fine.
The paranoia on mask is huge.
Is there? Yeah.
And always has been huge. remember, when I talk about history of lithography, then I tend to say, at some point in time, I talk about imaging-based lithography. Before that, before the 70s, you have proximity alignments where you put a wafer, you put a mask, and you put them in contact with the wafer, and you put a lamp on top of that. You wait a few seconds, and then you develop the image. The problem of that is, there are multiple problems, but the most significant problem is that after a few wafers, you can question the quality of your mask because you have resist sticking on the mask, you have defects being trapped, and then every next wafer copy that defect. So the mask was the most expensive part of the process, or one of the most expensive, one of the most critical elements and the cost of litho, because you have to renew the mask all the time. And so the mask industry was working like hell to make sure that every time you have a clean mask, so the customer could survive more wafers on that same mask, and the mask cost was big. Now later on it was developed by what we call proximity lithography, where you have a very small gap between the wafer and reticle, but still you have a big chance of trapping defects. Was already improvement, but the real breakthrough in lithography came in '73 when Perkin-Elmer was coming in with the one-to-one projection alignment. Today, Perkin-Elmer remainings are part of ASML. We acquired that in 2001, the remainings of Perkin-Elmer. So I know the story quite well. Also know the individuals quite well who did it. But that was the biggest invention in litho at that time, where the Philips guys and a few other guys were making steppers, but they were ahead of the time. The more cheaper way was you have a wafer, you have a mask, you separate them, and then you could almost manually push the wafer and mask at the same time on a fixed test rig through an elimination system, and it was always all right. But when you start scaling down the dimensions quickly, you still have an issue with its accuracy. So you have to correct. You have to get the correction, the overlay accuracy, but over the full wafer was becoming an issue. And there in the 80s, the GCA success was started, and also Nikon and Canon, where you start making a sub-exposure of a single die or chip, then go to the next place. So you have step and scan. And that evolved in step and repeat was the first embodiment, later step and scan, which is still today the case. And but at the same time, you reduce the pattern 5x, initially today 4x. So your errors are a bit more forgiving on the wafer since you do a demagnification.
Just one more question on that before we move on was what machine or process creates the mask?
That was an E-beam machine.
An extreme ultraviolet?
Yes.
Yeah.
Yeah, I remember, that's also interesting. When I started interviewing my job at ASML or Philips had, like I said, a business unit dealing with lithography, both E-beam and optical. So when I did my first day in March, I toured around to my new colleagues, and they all asked me, "Are you with the E-beam business or with the litho business, of the optical business?" And I said the optical business, and many were looking very sorry to me, saying, you picked the wrong thing. First of all, the optical division will be spin off to a joint venture, which I knew before my hiring. But the second point is everything below 1 micron will be E-beam. 41 years ago. And history is written, so optical is still there and E-beam is still there, but E-beam is way more time-consuming process, which you cannot afford for wafers, but for mask, it's needed because you have a chicken-egg problem. You need to have a translation from your design into a writing file, which writes the mask, and there where E-beam comes in.
I recently interviewed the CEO of Agilent, and I asked him, your equipment is used, let's say this 100 gigahertz oscilloscope that you have. How do you create products when they're already at the limit of possibility, engineering and physics possibilities. So I'd like to ask you the same question.
To stay on e-beam and optics, if you translate, first of all, the basic thing, the resolution limit for any tool is the smallest resolution, Rayleigh resolution limit, or upper resolution break-off limit is the wavelength over the opening angle of the optics. Now, when it comes to e-beam, you can translate it into wavelength also. You can translate the energy of an electron into wavelength, you get the same equation. And you found out that on e-beam, you have any resolution you want. Right? So you can make almost any resolution, except the smaller the resolution, the slower the system goes. And optics, and that has to do with the electron-electron interaction. But optics doesn't. But then optics has the following problem. In order to reduce if you look to the Rayleigh limit of optics, it's around the same number as chip manufacturing taking place. So our problem has been over all the time that every time we had to pick the wavelength, soon the wavelength was not suitable for making the next round. And that's why the sentiment when I joined, it was e-beam will come, because e-beam is way simpler. You have the wavelength already small enough, you can make anything you want. However, the economics was the reason why it never happens.
And I think they did.
And that's why the mask guys continue to use it. But the cost of mask, when things get smaller and more dense, including its inspection, including the materials, including the resist, becomes more. So that's why the mask is so expensive. And secondly, when you go into step and repeat, your defects become even more critical. Because if you do a one-to-one projection, you have, let's say you make 100 chips on a wafer, you have one-to-one mask, and you have a few defects, so a few chips are affected. If you have the stepper one defect on the mask, you will repeat it, you have 300 dies on the wafer or more, every single die will have a defect. So your defect limit is crazy, and that's one of the reasons why the mask is expensive. And I think if you would have a guy from the mask shop, he would not talk about the expense of the mask, the value of the mask. Because if you're a good mask, there's nothing more worth than a good mask, because you can just put it in a stepper and you use it, and you have hundreds of wafers per hour output. And
now each layer has its own mask, right?
Correct.
Yeah.
Well, that was also in the past.
And then how many layers is a typical chip today?
Well, at the time I started, there were probably DRAM 12, 13 layers. Logic 20, it's probably over 100 today, certainly including if you include the double patterning. So we now have layers, which in itself consist about multiple exposures and multiple process steps to get to the final patterning.
How did going back to the 5500, how did that do in the market? Was that a successful product, the past?
Yeah, so that's a good point. So there's one thing, there are a few things in my life determining the milestones in my life being litho, more or less. Determined the pace of the machines was wafer size and wavelength change. The mask change was very conservative, right? So master wavelength. And every time we do a wavelength change, it was mainly the optics, not the machine. Every time we do a wafer change, we have to put the whole machine upstairs, because the stages need to have a larger range, you need to have a bigger wafer handler, you need to have the machine scales up. So the 5500 to 2500 was a change from 4-inch to 6-inch wafers, and we were non-existing. So we get our initial business losing money for the rest of the decennium. When we towards the end of the decennium in the 80s, there was a need coming up for 8-inch. I took on that project at the time, and then I was solely responsible for the whole 5500 program. But if you change the wafer size, it allows you to rethink the machine concept. So what we did with the 5500, we are very eager to make a modular system. In fact, when we sold the first system to IBM, we had these milestones review with IBM at the time, and John Kelly, later member of the board of IBM and responsible for research, was at that time a responsible equipment engineer. That's how I learned John to great depth and detail. We were always working with IBM to tell them this system is different than other systems, it's modular, you can build stuff. And we didn't have orders of the system. And then I decided in early 91 to have a demonstration to IBM that we could build, the whole system works, we could build a system and IBM could trust ASML to do it. And then the Gulf War came into play. They canceled the trip because there was a travel warning from US citizens going abroad given possible hostilities during the Gulf War. And we were sitting, so what do? We have this meeting scheduled, everybody is sharp and everybody is going, and we still don't have orders for IBM. So, and that video still exists. We did continue that review, but then in front of a camera, which was today, like we do here, common, but at that time it was not very common to do these things. But so we ordered a video camera, we had the same demonstration of everyone, and we took the video, go on the plane, which was filled up with people fleeing back to the US, show it to IBM as if it was live. They were highly impressed them. And in that video contains a section where we could build the 5500 in 2 hours. So we had assembly engineer in the workflow was part of the show. They had these modules, because of modular, they could build the whole thing in 2 hours. And that impressed them such that it ended up in the order delivered to IBM and so on. And of course, while we finished the review and going for dinner in the Culinary Institute in Poughkeepsie, around 8 o'clock we were called by the cook who has his movie camera, of his television camera in the kitchen. So you could take a look at George Bush telling about the Gulf War, but we still have to return. So this is the story about the 5500.
Yes. Wow. Did you, besides IBM, did you have other customers for that machine? Was it a mass?
Of course, we had TSMC. So IBM was special because our initial customers were not established customers. Not Intel, not Motorola, not Toshiba, not TI. We were having the hungry customers, I call them, AMD, Micron, TSMC in the 80s. And they say, good, yeah, TSMC. TSMC was, and go back to the Morris story, in the 80s was not a big company. It was just a small outfit. But they were, of course, funded by Philips, so Philips had to say that. So we were supplying to TSMC and to those customers. And all three of them are today, I would say, winners of the industry. So we were lucky by having the customers willing to align with us, and we go and grow with our customers. And what's so special on the 5500, we were starting to attract big customers like IBM and later Samsung and Hynix. Of that time, Hyundai.
What were the sort of killer, I mean, in a way, was this a killer app for, if I may use that horrible expression? What is it that attracted these customers to your specific machine?
So the initial customers, believe it or not, were less interested in litho resolution because they were lagging anyway. They were on cost, which sounds for many strange for ASML because we have an image of being expensive machines. We are expensive in the sense of costing a lot of money, but we always talk about value of ownership. That means how much money you have to pay for how much productivity. And we believe we have been, over all those years, been champion on the cost of ownership, including today. That means the machines runs very fast. So it's the performance at high speed, which has been our differentiating element for a large part of our history.
Tell us just about some of the different disciplines that come together to make a machine like that.
I give you the 5200, 2500, which was my first project, which I did alignment and radical handling. When we start assembling the system, so we had test rigs. We tried to push modularity with test rigs, and we started building a machine, and we had the stage working. Then we put the stage in the system, and after the development process, all of a sudden, the thing was resonating. So the dynamics because of the speed, you start accelerating, shaking the whole system. You could not get to predictable conversion points. As of that point, we decided to do digital control, which was not custom, and we started to simulate the whole mechanical architecture. And we've been so sophisticated to this very day that we still think we are world leader at ASML with mechatronics, where through simulations, you can exactly simulate how things dynamically behave and how you damp it, so you can reach the speed and accuracy limit to its end. That has been one of the disciplines where mechanics, electronics, and software all comes together.
I know there are great programs like ComSol, for example, multi-physics simulation programs that I...
Yeah, so in the field of, back to my broad physics thing, if you talk about simulation, mechanical, dynamical simulations are very accurate. You can, if you know the construction, you can calculate the 3 significant digits, you know what the resonance frequencies are. And optics is also very accurate. When it comes to thermal, my competences with district heating, thermal is very difficult to model accurately because it's very difficult in its boundary conditions.
Right. Let's see. I want to ask you a bit about a very 10,000-foot question, which is, we mentioned the steps that ASML goes through every time there's one of two things, either a wafer size change or a wavelength change. Just before we get to that, I'm curious how larger wafer size, like ingots, what is the push-pull between the availability of ingots and the availability of machines?
That's a good point.
To use the ingots.
For ingots, you probably have better people talking about how to get big ingots, but the thing about wafer size is that most tools in a factory, the productivity goes by the surface of the wafer. A few tools are not benefiting from a bigger wafer, which are metrology tools, because they go by the square meters, and litho tools. So once we left the full wafer exposure and go to step and repeat, if you make a bigger wafer, you spend linear more time on exposing the wafer. So in a fab, metrology and litho are not scaling the same way as process tools. But since process tools are still the dominant of the fab at the time, a way to reduce cost was go to bigger wafers.
Yeah, and I mean, I think that's at least half of Moore's initial argument is as much about transistor density as it's as much about cost and efficiency.
Yeah, people narrowed, given the success of Dennard scaling, Moore's law is I consider the big law, and Dennard is a subset of that. But Dennard was so successful that people associate Moore's law with making things smaller. If you read his article more precise, I'm sure your colleagues here at Intel will help you there. He had his vision is phenomenal. What happens today in 3D integration and chiplets, he already partly predicted that in '65.
Oh, that's interesting. I will reread that. That's great.
Well, you don't have to look to him as only making things smaller. System scaling was in his article in '65. It's amazingly how visionary, accurate Moore was.
Yes, I think,
or Gordon.
Noyce, I think, also said something that kind of, if you read it the right way, can suggest chiplets in a way.
It's not explicitly, but that's not fair for Gordon to say he needs to read the same way we talk today. But if you look to his scaling, it's included there. Bigger systems.
And the emphasis on packaging as opposed to, it's just as important. Tell us about the importance of the supply chain to ASML over the years. Now
this is a difficult theme for me because I probably should go off on that we are infinitely smart and we deliberately choose for a supply chain system which makes our company better. The reality is differently that if you are small, you have 50 people, your capability is simply limited. And there's only one way to go fast in looking for friends. That means we were indifferent than GCA, PerkinElmer, Nikon. We're not vertically integrated, so we're working as much as we can with suppliers, not because we felt this was the smartest way of doing it, but it's the only way to get quick on your feet, which in the end helps us during all of our existence to move quickly. Give you an example. If you go from dry lithography to immersion lithography with water, you require process capability and competence in a company you simply don't have. So if you have a strong knowledge network to do that, you can make bigger progress. And that's how we moved always relatively quickly compared to our competition in these new fields.
And some of that was through acquisitions, right?
Well,
as well as hiring people.
Well, our acquisition strategy is twofold. So our first acquisition was to broaden our litho exposure competence beyond. So today, I think we have, next to the stepper business and big application business of a multi-billion effort by now, by trying to not only make the exposure, but also qualify the exposure, having feedback loop and having set up OPC on the mask, so we have a much broader competence base than just litho. Not every element, but where we feel we could make a difference. So, for instance, we acquire mask tools in late 90s, been enriched by Brian in 2006, which allows us now becoming one of the world leaders in OPC. And
can you tell us what OPC means?
Yeah, I was about doing that. OPC is optical proximity matching. If you're running short of wavelength, which we always done, that means you always like to have more resolution, but the resolution is not there given the wavelength. You're getting close to what we call the diffraction limit. When you're approaching the diffraction limit, the imaging is not linear for every feature. So if you have different features on the mask, you will not print them linearly. And now what you're now doing, but since it's optics, you can very accurately predict what that linearity is. So you give an offset to the mask, and they call it optical proximity matching. So your mask is not looking like the wafer, but when you image, it's the desired pattern. That's OPC. And why is that important? Because the OPC, of course, is giving you the credibility of your modeling, and that OPC knowledge, that simulation capability, now enables us to set up the system for maximum process window. So if you go to your video camera, which is in front of us, for most people it's only focus and exposure time, and that's about it. Make it very simple. Today, lithography is thousands of knobs in the machine, tweaking the illumination profile, tweaking the NA, tweaking the optics, tweaking the system. And now, since you could do the modeling in the OPC, that modeling capability helps you back to set up the system to get to a better process window control. And that, together with metrology, gets you much stable. So we are able to get to the edge of imaging much better with the holistic approach than we were initially without it. You were, in fact, shipping this tool blindly to the customer, hoping it would work. Today, you have more control on it.
And was that partially related to computational lithography?
Yes.
Yeah.
So, which is ahead of the AI. Today, computational litho also includes a lot of AI. But we were ahead of the time where we had the digital twin of our system, which we did with the optical modeling, we could optimize. And that reduces the amount of experimental tweaking enormously, and therefore the cycle time for our customers adjust very quickly the system, and getting quicker ramp up was very valuable.
Mm-hmm. So when they talk about bringing a lithography machine up, it's usually a multi-month process. In essence, they're trying to find the proper positions for all
Correct.
of those variables.
Correct.
Yeah.
And there the software and AI is extremely important, because at the end of the day, you can do this not to the end. If you have to explore this space experimentally, your ramp up is dead.
It's almost like a Monte Carlo simulation. There's
Correct.
a million different possibilities, and they all
to chip in yesterday dinner discussion with somebody who, from Brian at the time, I said, when I studied physics, I of course realized on this OPC, you can simulate a feature from the mask, how to look on the wafer. But you cannot simulate how a feature on the mask should look on the mask. Because the light, it's just causality, the light goes from mask to wafer, not from wafer to mask. So you could only do a forward calculation. Now that calculation is already very complicated. It requires you to solve all the Maxwell equations and all that stuff. But now you have to do it in reverse order. So what you're now doing, you calculate forward, you assume a feature. How does it image? Oh, I don't like the image. Let's go a bit to the right. You go to the right, you do the forward simulation again. And you put it in a loop, and you have to do it through the whole mask. It's a monster calculation.
Tell us a bit now about, I have a note here that you like to push 90% of the parts to the supplier.
Oh yeah, I left the supply chain.
Tell us a bit about that. Yeah.
So at Philips Research, we were accustomed to an optic supplier in France, Serco. It doesn't exist anymore. So my first project was, one of my first projects at ASML, I said we go to the alignment and radical analytic, but I also did take care of the old machine, the optics. So I visited Serco a few times. And that lens was a dual wavelength system, which is a very difficult to manufacture lens. And they could not manufacture the lens. So we are forced in my first year of presence to go to Zeiss and work with Zeiss on the optics. Zeiss had a history with GCA. If you read the history books of GCA, then Zeiss, they had mixed experience with Zeiss, to put it mildly. So Zeiss's business with GCA was going down, as well as Hitachi, and we were backing in, and we developed a partnership with Zeiss, where our competition, Nikon, Canon, said these guys don't own the competences, but the relationship between Zeiss and ASML developed such. This mutual dependency had a few advantages, because you had a very focused company on the optics and a very focused company on integrating the optics in the total system, including the system. So we had a number of key suppliers, Zeiss, Cymer later. Berliner Glass is a supplier of our wafer table. Skip the detail, but the wafer table is a very difficult piece. Next to the source, probably my most difficult piece, because the wafer table has multiple functions. It needs to be extremely flat. Any deviation of flatness gets you an accuracy and defocus problem. It needs to be wear resistant. It needs to be temperature controlled. We do that with water. And it needs to be extremely insensitive for defects. And that requires very complicated stuff. And in particular, when you go to EUV, on non-EUV and non-vacuum, you have a vacuum clamp, and EUV, you have an electrostatic clamp. That all together, water and thousands of volts, electrostatic clamps, and all the stuff is a very complicated part. So we had a few suppliers, and then a number of suppliers, like Zeiss, was successful enough to do it on their own, but some suppliers, like Cymer, but also Berliner Glass, were unable to make the necessary investment, so we ended up acquiring both companies. So being very selective in acquiring supply capability, we prefer to have the Zeiss relationship, and also meanwhile Trumpf, which are strong enough to maintain their own destiny.
You know, one interesting observation I had in reading about you and your company was how these two little ladies in San Diego who were winding tiny wires the width of a hair were kind of in the critical path. I mean, were they? Or
well, I was explaining my colleague this morning that the light source for both litho as well the metrology on litho, like metrology, but also alignment system, has been extremely critical to success. So I have been working with the folks in San Diego since the beginning. I know the founders of Cymer. We also had more laser suppliers at the time, like Lab de Physique in Göttingen, which were also initial there. But the source power at the time was only a few watts. Today, it's 100 watt. So I have worked with those folks for years to drive up the source power. And every time you do a wavelength change, you're in trouble. So we started with X-Cymer lasers with 248.
What is the lasing medium? Do you know?
It's an X-Cymer, which is a gas mixture. So you have a buffer gas. In the case of krypton fluoride, is the critical gas, the X-Cymer in the 248. For 193, it's argon fluoride. But the point is, so if an X-Cymer laser operating at 248, need to have this laser working at 193, you have to fill it with different gas, different gains. And I still remember when we were contemplating going to a different wavelength to 193, we're highly concerned about the source. We dropped from 10 watt or so down to 10 milliwatt or so in the first experiment. Today also, argon fluoride lasers are running at 100 watts. So we're very used with Cymer to drive to almost tiny power level, which are in fact economically not feasible, to power levels when you can do the high productivity, because the cost of the system require you to do a decent productivity, both from a footprint point of view in the fab as well as a cost perspective. So when we had EUV, we were naively thinking this is one more of the same, right? We start low and go higher. And this turns out a bit more tougher than we thought. And that includes the challenge of the droplet generator, where you're describing. And even today, the droplet generator is a critical element, because every time we have the droplet generator, we like to boost productivity. And so we like to increase the frequency, and then you need to decrease the droplet pressure. So what we did at Cymer when we acquired, we looked at it and said, Cymer could afford about 100 to 200 people on the source. But we said, with this momentum, we never get to the end. So we did a bold decision and proposed to Bob and Cymer to take the company, and we boost the whole team to 1,500 people. For a large part in Veldhoven, teaming up with the people in San Diego.
And then these employees, I think there's 1,500 you mentioned, they're devoted to ASML.
Correct.
And providing as a supplier.
It's a unique capability, and
right.
So we went to many learning cycles, but we were naively starting to think, we know how it works, and we'll quickly get to high power. I think only recently we get to 1,000 watt, but that was a number we never dreamed we could do.
And does that let you shorten the exposure time with more power? Or?
Yeah, sure.
Yeah.
Amongst others.
Yeah. And by the way, does that lasing medium dissociate, and you have to keep providing more
Correct.
gas?
So both the X-Cymer laser as well as the CO2 laser shooting on the thin droplet are gas lasers. And you have to refresh the gas anywhere, and then with CO2 a bit less of a problem, but certainly with X-Cymer laser to refresh the gas in time is an issue in driving the frequency up.
There was a great article in the Wall Street Journal, I'm sure you saw it, where they had your machine, and it was just in a great photograph. And I guess what I was wondering is, can you tell us, just for our audience, when does EUV begin? At what wavelength?
Yeah,
extreme ultraviolet.
That's a very good question. So our history, traditional of all lithographers, including Nikon and Canon, is what we call refractive optics. So you have a tube with glasses, and you have you transmit the light from the mask to the mask in the image. And you have to pass 30 elements, which are 60 surfaces, 60 materials.
30 little lenses, right, and pieces of
now
glass.
Little, can be big. And when you change the wavelength, a few things happens. First of all, when the wavelength shortened, the photon energy increases, which is fundamental, right? So the energy per photon is 1 over k over lambda. So the damaging, like you get sunburn yourself in the sun in the summer, the damaging to the glass can be significant. And the way to overcome that is reducing the amount of different glasses you use, which can withstand the shorter wavelength. And you're doing this to around 193 nanometer. There has been a limit, and then we contemplate going to 157. However, 157 until down to 193, we're using fused silicon provided by companies like Corning and a Japanese company called Ahi Glass. But then for 157, you have to go to calcium fluoride. And we naively started the calcium fluoride stuff, assuming we can fix the calcium fluoride. But while we're going through calcium fluoride, we learned that calcium fluoride is an intrinsic birefringent material. Means if you have any residual stress in material, it has different refractive index on different angles, which kills the image. And once we did that, we moved to immersion. But then we also stuck, because immersion allows you to increase the aperture from 0.9 to 1.3, but that was the end of the roadmap. Then you need to have the wavelength change. Or go to X-ray, or go to E-beam. And we all know that particle optics, I call E-beam, X-ray, no, not X-ray, E-beam and ion beam as particle optics are fundamental productivity challenge, because if you like to have charged particles in a close proximity, they start disturbing each other, blurring the image, and the only way to get a good image to have every electron one after the other going down to the image, but then your current is going down and your exposure time explodes. So this is the drama of particle optics. So we were eager to continue with optics. Now X-ray, proximity X-ray was abandoned, skipped that part, already quite early in the process. But then we need to go to a different wavelength. Now, as you know, EUV is invented in Japan and already in the 80s, so it's not our invention. But the way it goes in the industry, where people like Bell Labs and all later Livermore Labs did go their hand together, now you have to make a jump in wavelength from 193 to low enough to get you the benefit. And why is that important? Well, leaving 193, you cannot transmit through a lens. And now you need to have reflective optics. Every lens element, every surface has a transmission of 99.9x%. But a mirror, when you get below 200 nanometer, quickly goes to 30% loss per surface. So the point is, you have to look to which materials you can use to get decent reflectivity so you can maintain your productivity. This has been determined, and just determined to be around 13 nanometer gives you enough space to the 193 and still get your transmission. Because if you have a reflective optics, you're losing half of the optics. If you look to yourself in the mirror in the morning, if you're interested in yourself, you could look for infinite, but most people are not only interested in themselves, you need to image the mask. So you have to look over an angle to the glass, but then you lose half the angle. So you're losing half of the aperture opportunity already out of the box, first pass logic, and therefore you need to have sufficient wavelength reduction to get another train of limits. And we are already today approaching the diffraction limits of EUV.
And now, this obviously would have involved Zeiss very much in the design and characterizing of these lenses. Can you tell us a bit about the relationship with Zeiss just over the long term? I'm curious.
So, I told you that my first job was alignment and reticle handling. And I was having a side job on managing Serco. But then we realized we have to go to Zeiss. But the trick with Zeiss is that we had to modify the lens to get the alignment system through. So I was the alignment expert, so I was joining the Zeiss reviews from the beginning in the 80s. And I stayed to do that for 40 years. So every few months we go there for a few days, going through all the details. nitty-gritty deal. So we drive each other crazy over all those years in a joint effort. And given the success, where the German executives at the beginning were a bit hesitant for sharing this whole stuff, the joint success drove this relationship closer and closer.
Yes, and I know you probably don't want to rank your suppliers, but it's fair to say Zeiss is probably one of the more important,
Correct.
maybe the most important one, maybe? I don't know.
I
don't put words in your mouth. So.
No, I think I should not go on air by saying Zeiss is most important. Rest not all our suppliers are important, but there is a subset of suppliers which you deliver unique capability, and Zeiss is one of them.
Yeah, where you really have to work closely with them. Like
but there are more.
Like Cymer, for example.
But Cymer also, but they were running out of steam. So we had to infuse money into the company to scale up the team. In fact, the delaying timeline of EUV and the continuous burning R&D was problematic for the business at Cymer.
Right. What was their market at the time, Cymer?
Just litho. Us.
Oh, just lithography.
They were already then 100% of a supplier, which we were very comfortable to allow because the company was able to drive the roadmap on their own. But that broke down at EUV given the size of the R&D required on EUV because of the disruption between an X-Cymer laser and a CO2 laser and a droplet generator and a tin droplet.
Yes. Here's just a little financial question.
So back to your tin droplet thing, your wire at San Diego. I forgot to say that.
Oh yes, sorry.
We did industrialize that manufacturing process, which you now not depending on the ladies. You automate it. You still not do it right out of the box, but you do it the same. And now your learning becomes more sophisticated. So that's how do we dealt with the droplet generator.
Exactly. Do you want to give us a quick lowdown on how immersion lithography works and why it is a step forward in chip manufacture?
Yeah, so immersion lithography is known out of physics books by anyone. But I at the time could not imagine by putting water into the system I could deal with the process side of it. So we pushed it out, and we rather took the challenge of trying to make 157 work than getting immersion work. Until we were struggling with 157, once we had a following insight. Because of technical details, a last element between the wafer facing the wafer was flat. So we have flat wafer and flat surface. Now if you go in the swimming pool and you have your goggles on, that's a flat surface, and you look sharp. If you take off your goggles and you look in the swimming pool, everything looks blurry. This is the problem of anyone not having a flat surface. You have to correct the strength of the lens in order to correct the aberrations. If you only have a flat lens, you just shift the focus a bit, but you can have a decent image. So what we did in immersion, we did experiment immersion not on a new lens, which would require us to develop a complete new optics. We're able to get a flat lens, put water in between, and with the same aperture, same resolution power, we could double the depth of focus. We could improve the focus. So we were able, compared to our competition, moving much faster for two reasons, because of the flat element, and the second element we didn't discuss yet. We talked about the revolution of wafer size before. 6-inch was my first experience. 6-inch was my first experience in '84. 8-inch was IBM, the IBM machine. The 12-inch was in 2000. And in 2000, we said, okay, we have these big wafers, but now we need to get another productivity boost. And traditional litho, you have the wafer coming in, you measure where the pattern is, and then you shift the wafer on the lens and start exposing. That measuring of the wafer costs you time. So we said the lens is most expensive part in the system. So we maximize utilization from the lens to make sure it always sees the wafer. So we put 2 stages in. So one stage measuring the incoming wafer, the other stage exposing the already measured wafer. And then we swap the stages very, very quickly. So what it does, it decouples the metrology problem, the alignment problem, and the leveling problem from the expose problem, and we could work in parallel. That, in fact, was the final push to our competition, where they pushed behind the competition on all of the products. So our productivity was unbeatable by then. And also, it allows us to get more accuracy because we could measure more points because we did have more time, right? We had the whole thing in parallel, where normally the measurement and expose is sequentially, so you have to compromise it. Now you could spend more time. Now the final thing, which when we have immersion, if you have your metrology around the lens and you put water in the system, your metrology doesn't work anymore. But we had our metrology on the dry station next to the lens. So we could move very, very quickly to immersion because of the flat lens and the fact they have a dual system, which of course you should write down in the History Center. This is all wisdom. But you can imagine there was some luck in this also.
Yeah, I mean, in a way, it's sort of counterintuitive, and adding water makes something clearer. But I guess
no, it's the swimming pool example.
Yeah,
try to do it yourself by having goggles or without goggles, and try to look without goggles. You don't get an image because the refracting power, the index of water is substantially different, 50% different than air, and that's why your focus capability is simply not able to change to compensate for that. Or you focus your natural lens modification will not be able to.
And I think some scientific microscopes also have oil immersion lenses.
Yeah. But so that was all known.
Different thing, but
that's the same thing, same principle. If you have oil in between, all have even a bit higher refractive is better. But we did start water, and we didn't go to oil because oil. We had a trauma on the oil stage back in '84 when we had the electrical stage versus the oil stage.
Just went everywhere.
Yeah,
the oil.
The thing smells like a car shop if you have a problem in the clean room.
Oh no. What about post immersion? Is there technology after that? Yeah, tell us about that.
The first thing I like to say that EUV, which we started to talk about, invented in late 80s, being exercised on Bell Labs, been taken over by Intel and the Consortium, the EUV LLC and the Livermore Labs in the late 90s. We were already having defined EUV as the successor of optical in '95. And we had a small effort in Holland at the Scientific Industry Institute in VOM in Rijnhuizen by a gentleman called Fred Bijkerk, who was amongst the first making EUV exposures in the early 90s. So that was just at reach.
Was this a university lab?
I think it's a science institute. It's FOM, fundamental. I think it's part of the university system, either in Utrecht or it doesn't exist anymore. Today, that whole group is transferred to the University of Twente and working for a large part for Zeiss. But they were expert in coatings, making sure it gets the transmission, and they're still active in that. But we were clear that EUV would be quite a substantial adventure. So we were clear that we have to extend optical litho as far as we can because of cost reasons. And that was a self-fulfilling prophecy. First of all, we start extending, by the time we defined EUV as our destiny in '95. So there was, I still remember the board meeting where I took on the role of CTO for the first time in probably '94. My first question was, show us the roadmap for the next 100 years, so to speak. So I had EUV on there. We call it that time soft X-ray, but the marketing guys found extreme UV a better market word because the hard X-ray was a failure. So we call it that kind of soft X-ray. We successfully we didn't have 193 on the roadmap, on the execution roadmap, and not immersion. So we were extending EUV with immersion and 193 before we ramp up EUV. So we were busy on the basic thing, and we created prototypes and research. So we started a research program in the end of the 90s, which ending up at both the IMEC and Albany had a prototype tool in 2005. 2005 was the same time we made our immersion transition. And then still it took more than 10 years to go to initialize. And the reason for that is that we found out EUV is too expensive. If you calculate the tool cost, then a tool was costing you below 10 million, a DUV tool, but an EUV tool was creeping already towards 100 million. We thought this was too expensive. So then the world was saying, if EUV not comes, how do we make sure we shrink? Double patterning was the answer. So double patterning saved us in multiple aspects and saved our customers. First of all, our customers could continue to shrink without having new tools, new technology. The second of all, double patterning is not cheap. Because instead of the system going once through the litho machine and the process tool, it needs to go at least twice. And in some cases, over time, at the end of double patterning, there were layers requiring 10 exposures to complete. So it changes the cost of lithography changes, so that at some point in time, EUV became cheap. And that's how the transition, in the end of the day, happened. That EUV was too expensive and too difficult, to be fair. But then, while double patterning was saving our butt because we could ship, instead of less machines, more machines, because of every layer requiring now multiple exposures. And it gives us the time to finish EUV and also offer the EUV as a cost reduction rather than a cost increase. Mm-hmm. And this is not only cost reduction on cost per exposure, but also cost for the integration, because it's also the process layer and the cycle time is going. I mean, Intel has been quite vocal in the press that their late adoption of EUV put them at disadvantage compared to TSMC.
Yes, exactly. What made EUV economical? Was it from the customer side or from your your side?
First of all, now I think we could have done, still can do a better job making it economic by reducing the cost, and we're still doing that. But the biggest leverage on that was source power. That's why the acquisition of Cymer was so important. Right. So the source power, but the source power was a major challenge because the physics around source is quite complicated. And if we know everything we know now about sources 15 years ago, we would go much faster. But this was an experimental stuff to get the right frequency, the right droplet positioning, the right metrology, the right gas mixture to make sure the tin is not clogging the mirror and all that stuff.
Thank you for bringing that up, because this is one of the most interesting parts of your machine that I want to dig into, which is the tin is it ablation or whatever you want to call it, and the use of vaporizing tin in your machine. First of all, who thought of that? And secondly,
the vaporizing tin is invented by the tin itself. When you are a droplet 30 micron diameter, and you get a source of 30 kilowatt shoot at you, you have no choice to evaporate.
I suppose, yes.
You have no choice. Right. You're gone.
But I mean, choosing tin, for example, how did that come about?
That's already done very early on, even before Cymer. So it's part I skipped. I couldn't afford. So Barrow the Livermore program we had two source principles. Is plasma, laser plasma induced, and discharge plasma induced. The laser plasma was a laser shooting at the material. You collect the light and you send it over. The discharge was like a discharge lamp. You have a tube with gas, and you make a discharge, electrical discharge, and that helps you.
Like a flash lamp or something?
Yeah. And we did first the Alpha Demo tool in Albany and an IMEC. The first tool was equipped with a discharge source, because I couldn't afford a bigger. That was done in Philips Research. Philips Research had a major capability in Aachen, in Germany, where they do the research on lamps, and it was synergistic with them. So remember again the outsourcing competence and so on. So we're able to get 5 watt or so, or a few watt, out of a discharge source, but we couldn't scale it up. And the scale-up was, of course, experimental material. So on this discharge source, we already did experiments with what material. And then we found out that tin has one of the highest conversion efficiency going from heat into EUV. And now the heating process you do with discharge or you do with laser.
So probably from early spectrographic studies in the 30s
Correct.
or something, somebody
It
noticed
was already scientifically documented,
right,
but not exercised.
But I mean, it seems so just fascinatingly complex.
Well, the problem is tin, you need that fluid tin, so everything works at 273 degrees, which is the melting point of tin. And then tin likes to be everywhere, right? So, which is the other problem.
Yes, how do you decontaminate your chamber?
This has been the major issue of my life.
Oh, really?
And also, when people say, let's go to a different wavelength, say good luck. Because you have to redo that whole exercise. Experimentally, because the modeling, remember, mechanical dynamical modeling can be done quite accurately. Optics, when it comes to thermal, plasma, it's very experimental. So you have to explore the space, for a large part, experimental.
Yeah, and you mentioned earlier that the thermal engineering of the system is very precise.
Because you have to deliberately not meet the melting point, or you have to meet melting point. And if you pump in 30 kilowatt of heat into the system, you need the cooling system and everything right to make sure you get the melting where you allow the melting to happen, and not having the melting where you, or the gas phase to fluid phase, that means the condensation points. Mm-hmm. So it's a big engineering detailed issue. I'd like to make 2 points which relates partly to your questions you listed, is how the world has changed during my term in the industry. First of all, when you look to IBM, you look to Bell Labs, you look to Hitachi, Toshiba, they all have vertical integration strategies, meaning you make your manufacturing, you design your product, you manufacture the product, and if you need special tools to manufacture, you make them yourself. That's how the history was. If you look to Philips as a prime example, they were 100 years in bulbs. And the reason they were successful in bulbs, because they could build an efficient machine who can create bulbs. And a bulb machine is multiple times this room. And let's say sand goes in and bulbs coming out. That kind of stuff. And they were so good at that nobody could copy that. So this principle was applied everywhere. So that's how Philips started in the early 70s, by thinking about how do we make the next generation litho for use inside Philips. Nobody thought about going outside Philips. And what happens just before mine arrival is that the industry started to realize, when you standardize the process in the factory, if every chip maker making CMOS or silicon wafers, why would this supplier, this manufacturing, that manufacturing invent independently the same machine? So you then saw the equipment industry coming up. Applied is one example of that. GCA and others. Let's not let customers wait until let customers depend on a supplier gave them the right equipment, which was not done before. Now, in the case of Philips, they were relatively slow in adjusting this process because they have such a huge success with the bulbs. And knowing that when they control the manufacturing, they control the destiny. So they were probably hanging on longer than some of the other players. But in the end of the day, they convinced that they have to put the same model, so they had to spin off litho. Because Philips, being a producer of chips, will be unlikely successful, Philips, supplying litho systems to other competitors. If you like to learn this story, go to Morris Cheng. He has a great philosophy when it comes to foundry business. Foundry business should not design chips. You should not compete with your customers. Now back to my time, 20 years earlier. Philips could not compete with their customers being litho users. So we have to put the thing separately. In fact, this was a major issue at the beginning Philips had a big say in that, and customers just second guess, will Philips send us the best machine or the worst machine? So this was a bit of the initial struggle. And of course, history has done. So today, the supply industry has a major issue of manufacturing. In fact, this whole model evolved. And Morris' dream of not even chip makers are not making the chips because the manufacturing is being outsourced to TSMC. So this whole supply chain model has been now reached up to our customers. And at ASML, when it comes to our supply chain, we didn't have to compete, so we had no choice in the first place. So we, from day one, rely on the supply chain. So I'd just like you to notice the change in industry, which has been major, which ASML was part of it, not only limited to ASML, also to our co-solution providers as well as our customers. The second element I'd like to share with you is these big corporate institutions, research institutes. You have big labs, national labs, Philips Research, Bell Labs, stuff. All major conglomerates depend on inventing this solution in the lab and then bring it into industry. What turns out in my term is that this efficiency by the research driving the industry runs out of momentum, also around the time I joined. You can look to what Philips Research is today compared to what it was. You can look to Bell Labs, which now owned by Nokia, what it is compared to what it was at the time. I've been many times at Bell Labs. My first visit at Bell Labs, when I was negotiating the e-beam system, Bill Brinkman was picking me up and showed me on the display behind the entrance, showing me all the major Bell Labs fellows, where a substantial amount had Nobel Prizes, right? I was thinking I'm working for the wrong company when I would join. So Bill Brinkman toured me around and showed me the transistor lab, which, of course, being a young physicist, you've been thinking, shit, this is the place where everything started, right? Now, of course, it turns out differently that this whole major research labs couldn't connect to the industry. So what you see during my term, and Intel is one of the companies who never had this big central research. You have your own research, compact research, with a knowledge network who you go to for certain topics. And that's how all major companies work today. So central research is over and you have the business driving it, but you still need to be careful by understanding what your next step is. And you need to have your knowledge network in place to make sure you know where to go for which questions. I give you the example of the Immersion system at ASML, where we need knowledge on how you deal with water. Those are two stories which I think are partly touch upon why things happen the way it happens in the early days.
Exactly, and the coupling between ASML and the customer just seems so tight. Like you really listen to them and their needs, and almost co-design. Is that fair to say?
No, that's there's TSMC co-design. Perhaps you can make it that way. So what I have been developed over time in these customer consortiums, which we already had in the 90s. Where we invited customers in design reviews of our system. So we invited as much as we can customers in our design reviews. Not that they co-design, because if you know how to make chips, it doesn't mean you know how to make hardware. If you know how to make hardware, you don't know how to make chips. So these reviews were more or less a mutual education. And in this mutual education, you trigger points at the other side he didn't thought about. They say, well, we can do it this way. And sometimes say, well, you do it this way, but could you also do it that way? And then this was on our side. So these reviews turns out to be quite effectively keeping the customer up to speed where we are, but also were very inspiring for the teams at ASML, which we had exposed the customer to drive their innovations. So this has been quite successful, and this has been accumulated probably initially with EUV working with the national labs and with the EUV LLC, as well as with the Philips research, which was doing the first initial light sources. But later on, it has been institutionalized. In 2012, we get the co-investment program where Intel wants to have 450 millimeter wafers.
Oh, yes, tell us about that.
And we try to have an alignment between the big three customers, Intel, TSMC, and Samsung, where the big decision makers were Kwon at Samsung and Morris Chang at TSMC and Bill Holt in Intel. And TSMC and Samsung demanded to not only do 450 but also put EUV. And this was a program where we allow customers to get close to 25% interest in ASML, which for that money we could put on top of the R&D budget, so we could gain momentum. And our customers, as long as we spent the money well, we get the money back for the share value. So the money was not wasted, it was just the shareholders' money was 1.3 billion on top of the R&D budget. It was quite successful. And then the second element happens here is that this consortium, you sit together with those three customers and you talk about 450 progress and EUV progress, and all of a sudden it turns out to Intel that nobody was really interested in 450. So 450 program was cancelled a year after the program. So the majority of the money of that consortium was spent on EUV, which was very important, also helping to focus the company. I think I sometimes tell our co-solution suppliers, we probably were the company spent the least amount of money on 450 on a relative scale because of this consortium. And that consortium then continues in different form to High-NA.
Interesting. So the sort of failure or ending of the 450 project helped you on the EUV project.
So TSMC and Samsung didn't like us to have Intel only have 25%. They were okay with 25%. We were not interested in Intel ruling our roadmap. We have seen that with SVG in the early days, which was not helping. So we were eager to put Samsung and TSMC part of it. They were, of course, curious how Intel would go around with 450, which the value proposition was highly challenged. But they said, okay, if we do this, we need to have EUV part of it because that's important for us. So Samsung and TSMC pushed the EUV part of it. And then if Intel asked, we should spend more money on 450, they were saying, why would we do 450? Tell us why we need to do 450. So 450 didn't work because of this consortium. Or, well, not because of this consortium. The realization in the industry that 450 would not come was partly created in this consortium, in this close cooperation. So this close cooperation with the customer helps you to focus and working on the things which does matter, rather than go off on a tangential.
Yes, exactly. Can you tell us what percent of ASML budget is devoted to R&D?
So I have a simple rule. It needs to be between 20 and 10%. And the 20 and 10% is depending on the business cycle more than anything else. So in fact, if you spent 1 year 15%, you could spend up the next year with the same spending 20% if your business go down, or the business goes up and you're ending up spending 10%. So I have a slow adoption rate to the business between 10 and 20%, and try to stay within those boundaries. But we really like to get stability on the long-term roadmap. It's probably differently how our American colleagues did manage budgets, but.
How long did it take you in terms of NRE, as they call it, engineering, non-recurrent engineering, to design the latest machine?
No, billions.
And
we're spending.
Let's say
we're spending $4 billion a year.
$4 billion a year in
today
R&D.
In R&D.
Wow.
Yeah, it's not that difficult. You take the 30 billion turnover or so. You take 10%. That's already 3 billion. So it's all consistent with the numbers I showed.
There anything about the Dutch labor climate that is relevant to ASML?
It was relevant in the past. So I explained yesterday the success of the company determines partly the success in which you can hire resources. Today, the Dutch are almost not depending solely, ASML is not depending solely on the Dutch labor market. In fact, we have the European Union, so everyone in the European is free to work at ASML. So we have people from all over Europe interested to work at ASML. But we also have people all over the world doing the same thing. We have over 120 nationalities on the Prime Office. I don't think there are many companies with that broad capability, and that is because of the success of the company itself. And I saw it changing over time, where in the early days when we were 50 people, you could not convince people because you always had the question, how do you know you still exist next year, right? Yeah. So they were all very much concerned about job security. That part is gone. But at some level of success, in particular after the IPO in 95, you got more and more senior engineers and capable people be interested in working with you. So success attracts success. And our pond was not limited to the amount of people present in Holland. That also softened, of course, by the international supply chain.
Fascinating. Let's see.
And also our acquisition with Cymer and SVG helped us, and also Brian helped us on major software, not only focused in Veldhoven, but also in other places in the world. So we tap in different places.
I wanted to ask you if there were questions I forgot to ask, since we're at this point now, and I'm looking at your, I think I've covered most of them.
High-NA. Yeah.
Yeah.
We can do a...
Was there anything else you'd like to...
There was not on the list, but it's okay.
Yeah. Yeah, please go ahead.
So, I told you I'm very hot on long-term roadmaps. Defining also long-term roadmaps with the customers, which different customers have different long-term breadth, but Intel has been a very valuable source in terms of defining a long-term roadmap and the discussion there. So I still remember, we did start low NA, 0.33 NA, physically in the research lab to develop in the late 90s. But in 2008, I gave a presentation at SPE. Also, Zeiss also gave a separate presentation where we announced already high NA. So going from 0.33 to 0.7 plus. We had great difficulty designing the right concept with Zeiss. So it took us several years. And also, we were not in a hurry because the low NA was first. But around 2015, we defined a concept where we using asymmetrical magnification to deal with a specific issue on angular sensitivities and all that stuff, details, where we find the concept where we get a high productivity, high NA systems. And to make that, we have to increase our infrastructure at Zeiss at high cost, because these mirrors need to be bigger. So just, I didn't tell you that, but one of the things when you go from lower NA to higher NA, the size of the optics go infinite, theoretically. So an aperture of 1 is an infinite light length. So you have to stay away from 1. And one is the refractive index of air. If you go to water, the refractive index is 1.5. You have to stay, the limit is around 1.3. With EUV, you have similar limits. One is fundamental limit. If you like to have a uniform pupil, the thing is low. So EUV optimization is more complicated. So in particular EUV, when you increase the angles and you need to be reflective, a lower NA goes like this, and higher NA goes like this, it blows up. So the size of the optics was a concern. It requires to reinvent the infrastructure. So Zeiss had limited appetite doing it given the cost. And then we invented a contract with Zeiss called the High-NA contract, where we took 25% interest. And we agreed with Zeiss making then the High-NA system. But then it was very clear, the board agreed with me that we start a major program called High-NA, but we need to get our customers on side. And we, at that time, 2016, didn't have our customers operational on 0.33. So we continued to work on maturing 1.33, and one of the key milestones is that we need to get 250 watt demonstrated to our customers in order to call 0.33 a viable cost, because if you don't get the power up, your cost point is too high. And we were now giving ourselves a year or so time with the board to get the orders in on High-NA, to extend the consortium, so to speak, to High-NA. But some of the customers were not willing to move there, given the fact that the 0.33 was not even running at decent productivity. And that came together in the late 2017, early 2018. We just get the 250, and we get the orders on High-NA, and that's the start point of High-NA. That's how it turns out.
What was the appeal of High-NA?
Well, we skipped that, partly. So we talked about resolution is about wavelength, right? The real math on wavelength is wavelength over opening angle. Like your camera lens is not wavelength because it's what you have, but in the camera you have the f number. It's the same as opening angle, it's the same as aperture, it's a different notation. So the shorter the f number, the bigger the lens, and the more expensive the lens will be. In particular, when you get your long lenses, you get these things, right? So same in litho, things blowing up. So you have your wavelength, which is fundamental, and if you assume you could drive things to infinite big, an aperture of 1 gives you the limit of resolution at a given wavelength. But you're starting out with a lens with a much lower NA. So our first aperture in the 84 was 0.28. Was almost a quarter of the total range available. So we pushed over the years the aperture at a given wavelength. I think our biggest aperture is 0.91 dry aperture. It's a 248 system. But that's already a big lens.
So the lenses are getting huge at this point.
So the NA scales the lens is crazy. Yeah. So I told you about the wavelength choice. You like to go to the shortest wavelength because the shortest wavelength allows you to get the resolution, the shortest, smallest opening angle, the most compact optics. So hence the 0.33 was still a big lens, but sizable. If you increase that you double that to 0.6, 0.55, you almost, which is the aperture of High-NA, you almost double, triple the size of the optics. And that has been the challenge, that you need to have the cost.
And from the customer's point of view, that increases throughput, or
no? It increases it increases floor space. So you need to make up. So I still remember Keenam Kim going to say, Martin, your math doesn't add up. So what do you mean? Say, I need to have the same wafer per hour per square meters. So if you make twice as big a machine, I like to have twice the productivity, because I don't like to get down on my I don't like to go up on my floor space. My fabs is big enough. So the whole thing is economics. Like I said in the beginning, the success of ASML is that we get, in the beginning, we put the economics prime. It's good that they have a good lens and a good overlay, good imaging, but it needs to be affordable. and that mainly done through productivity changes and cost changes.
I'd like to touch on software because that's a really key part, especially with your new machines.
Correct.
And tell us a bit how software is used in ASML machines.
So software has been the biggest department, if you will, biggest competences in the company. In particular, also if you add the OPC group here in Santa Clara with it. So first of all, it's our ability to simulate the system, which is key. So we understand by model, and so we can calculate all the knobs what the impact is. Then the second point is that knowledge now need to be used inside the system to drive the subsystems. So the model gets you the application space and you know how to set up your systems. But now you have to modify and add knobs where you can to modify the image to optimize the total. And that is control software, which is the other element. Now, one element on control software is stages. What we, for instance, I told you about the early days, where we start testing a stage on a test stand, we put it in a machine, it gets unstable. And that has to do with the interaction between the different mechanical parts. So you get resonance frequency in the way and you cannot control it. So the same as you make a step with a wafer stage, you put a set point out and you drive the stage to a certain speed, and it takes you time to get there. It takes you time to get the servo settling out and get a stable profile. But that settling is your productivity. So what we did, we're not making digital twins of the system, we're making digital twins of the mechanics. To get detailed modeling. And now what we now do, we know how the system behaves, and now we can anticipate the damping. So we go straight to the set point and have zero settling time. Of course, you do the feed forwards. You do all the feed forwards, so and the more detailed you are, the better successful you are in doing this.
What is the reality behind copy exact?
We never had that.
Okay, because I read.
We never had it.
Okay,
it's an Intel terminology, which I believe by now Intel will also say it's gone on Intel. But Intel had such a successful execution history on one node after the other node after the other node. I mean, people talking about Intel as a major struggle at the moment, but you also have to be fair on Intel history. They have been ruthless on the execution for years. And of course, when you have that, if you're a successful company, you're making every 2 years a new design, which lets you to more advanced chips driving our industry to date, that you're making mistakes. And the mistakes you fix by fixing it very quickly. But if you have a big operation, you have many places where people invent and do changes. And soon you don't know what this guy doing for that guy doing. So then they say, they inserted 20 years ago or even longer, the copy after one major hiccup in production. They say, we can only do copy exact. That means you release a configuration for production and you keep that configuration the same, whatever happens, and only we determine what to change. This is, I'm sure if you talk to TSMC, some of that is still in the foundry business as well with their customers. But Intel potentially did it go a bit over the top on this.
Well, in terms of technical management, do you have a philosophy for how ASML has tens of thousands of people now? How do you?
We could have a bit more on copy exact. To be fair, because to control that large, because we talked about 4 billion. It's about 40,000 engineers, 40,000 employees, about 20,000 engineers, not counting the supply chain. And to coordinate that is another major issue. Yes. So another element of growth, the engineering organization, is what I call system engineering, which also helped us in modularity, like I told you, the IBM modularity, where we showed the system to be assembled in 2 hours. One way to do it is you have a small group. Out of that big group, you select a small group who does the system design and cut the system into subsystems, which has defined interfaces. And now you could allocate those subsystems to smaller groups with less communication challenges. So and that's one of the reasons why the big research labs failed. You had in the past the existing stepper, the old stepper has been designed and made by 10 people. You can't do that anymore. Things are way too complicated. So today the trick is, in any complex system, you start cutting it in pieces, potentially even on several levels. So you assign those blocks to people, and then you need to start integrating it. So I think ASML has become over time more an integrated company than just with modules coming from suppliers and subgroups than anything else.
It reminds me a bit of...
And then be ruthless on the interface definition, right? You need to control the interfaces. So the copy exact needs to be applied there. That means try to control, because if you don't control the interface, all the pieces come together. They don't talk to each other, right?
In some ways, it reminds me of Boeing's earlier model, like on the Dreamliner, where they said, we're not going to make so many things in-house. We're going to...
The nightmare liner, yeah.
And it turned out very badly. But you have pulled it off brilliantly. And
the brilliance is a bit overdoing it. I'm fine if you put this in our history book. This is brilliant. But if you've been close to it, brilliancy has its limits everywhere you come.
Understood. And, from what I've read, it was a very stressful career, if I may.
Correct.
For you.
Correct.
And for others.
Correct.
Do you have any thoughts on that? And
yeah, I killed myself at some point. Almost.
Yeah.
But you can talk about after the fact.
Okay.
But when it happens,
Yeah.
When it happens, it's not nice. But so for the major struggle for me, if you go back, was this IBM struggle with the 6-inch system, which was before the IPO, so we didn't have the money. Philips was calling out of crisis. They had a major business inflection point. They called Operation Centurion, where they had to improve. They're cutting things out of Philips, but we were spenders. But we had short in money, and we didn't have the IPO yet. To try to get that machine working with a limited resource was quite stressful.
Yes.
But I'm sure everyone has this period in his career when he looks back and says, well, this was potentially a bit too much. And not only for yourself, but also the pressure you exercise on your team. So it was not only me, it was also some of the team members, which probably, looking back, say, well, we could have found maybe a bit differently with less stress.
I just think, to great accomplishments take great efforts, and sometimes that's what happens.
Yeah.
So do you have any advice for young people who are interested in technology or integrated circuits and computers, that kind of thing? What would you tell them?
Yeah, so this question I get regularly. And I am, in the time of AI, I could have many advices, but I would urge young people to choose a competence which they can get good at, they can make a difference, they can contribute. You have lots of young people who loves to go to management and to MBAs and stuff like that. I'm not a big fan of that. I always thought, I probably said it in between, I don't consider the business side as that complicated as physics. So you can do this business side also on the side. Maybe people would argue that, but to have people who understand how to make a difference to a particular problem, I would, if you're young, it's the best chance to do that. If you're my age, you're running on your experience. Now, I have a very rich experience, luckily enough, so I'm one of the lucky guys being through the ranks from beginning to end. Probably a lot of people don't have that. But in order for you, you have to make sure you can make a difference to where you are. And excelling on the content is, in my view, the best way to do it, rather than just doing the organization side of it. Organization side will come over time.
That's wonderful. One of my nieces, I asked her when she was about 5, what do you want to do when you grow up? And she said, I just want to be useful. And that sounds like a wonderful...
That's probably true for everyone, but I was a bit more specific on how to be useful, trying to be on the content so you can make a difference.
Yeah.
It's a bit more specific.
Yeah. Well, Martin, thank you so much for joining us today. It was a delight.
Thank you.
And thank you so much.
Thank you very much.
Yeah.